is learn a different way to find limits. So, dang, not now. Okay, so how did you find this limit back in chapter 2? What did you do?
Well, the first thing I tried was plugging it in.
The first thing you try is plugging it in. That's a good strategy. And why is plugging 2 in a problem?
You get 0 over 0?
You get 0. I think you get 0 over 0. The denominator, you get 4 minus 10 plus 6 makes 0, right? So, well, you said, okay, well, hopefully I can simplify this. And this one isn't so bad. You factor it into x minus 2, x plus 2. How does the denominator factor? You always get this x minus 2 and x minus 3. But you can think, Rachel, is that you could even fill in your signs first. Like it's got to be minus minus because it adds to a negative and multiplies to a positive. Michaela, just in case you missed it, test corrections if you want to do them are due on Monday. Okay? All right, so now the x minus 2's can cancel, and you get the limit as x goes to 2 of x plus 2 over x minus 3. Can you plug in 2 now? Okay, and when you do so, what do you get? So negative 4. And that one's not so bad because you remember your factoring formula, right? Like those are pretty easy to factor. But the next one sucks a little bit, right? Because you all forgot how to factor a cubed plus b cubed, right? So I'm going to teach you a different strategy today so you do this without relying on this factoring thing. So this is the same thing. Here's the factoring pattern just one more time. It's going to factor into x plus 3, x squared minus 3x plus 9. And then the x plus 3's cancel, and you have the limit as x goes to negative 3 of 1 over that stuff. And I think, what do you get when you plug in 3 now? I think it's 1 over 27. Because negative 3 squared is 9, right? And then you this negative multiplies by another negative, which makes a positive also, another positive. My guess is you missed the middle negative sign. Is that correct? Okay, it happens. Okay, so 1/27. But that sucks because that's a tricky factor pattern and it's hard to find. And this also doesn't let us deal with stuff where factoring isn't an option. Like we had we had factoring algebra, which involved expanding, stuff like that, right? So the rule we're going to use is something called L'Hôpital's rule. It's French. I'm probably saying it wrong, but it's not La Hospital. I know that, okay? I can know that much is not right.
You're actually pretty spot on.
Yeah? Okay. So what this says is if you have a limit where either the limits of 2 functions go to 0 or the limits of 2 functions go to infinity, that is called indeterminate form 0 over 0 or infinity over infinity. And that's called indeterminate because 0 over 0 and infinity divided by infinity are not consistently one thing. Kind of like they're not defined, but they're not defined in a specific way. And if you have a limit where the limits of the numerator and denominator are both 0 or both infinity, then you can find the limit of the ratio by finding the limit of the ratio of the derivatives. So this says that those 2 limits will be equal. So for a quick example, the last one. So the last one that we did was the limit as x goes to negative 3 of x plus 3 over x cubed plus 27, right? That's what it was. That's okay. That's what it was, right? Now what you check and see when you plug in negative 3, is the numerator 0? When you plug in negative 3, is the denominator 0? Yes, okay, well then you can apply this rule, and this rule says this limit is equal to a limit where x goes to the same number, and the ratio is now the ratio of the derivatives. So what's the derivative of x plus 3? What's the derivative of x cubed plus 27? And now can you plug in negative 3? Do you get the same answer?
I
It's nice, yeah. Okay? It always works when your limits are 0 over 0. If the limits are not 0 over 0, this method fails and you cannot use it. Okay, so you should always be doing like what we got here. I'm not column. Devin said, right? Yes?
Yeah.
Okay. Names on the spot are hard. Always check and see when you plug in your numbers. Like check and see, can I plug those numbers in first? If you can, great. And if it's 0 over 0, you can use this rule. Okay? And you can always use this rule and never factor again if you really, really want to. Unless I like specifying directions that you must factor. But maybe I wouldn't make you factor something like this, because realistically speaking, knowing that factor formula is not super important. I mean, this is a more general idea. And also it works if you have infinity over infinity, and the infinities don't have to have the same signs. It could be that the numerator goes to positive infinity, the denominator goes to negative infinity. That doesn't matter. They just have to get infinitely large. Okay, so let's do a few. So only use it if your limit is 0 over 0 or infinity over infinity. If not, method fails and you fail too. Oh wait, was that harsh? Sorry. Okay, so first check and see, is it a 0 over 0? If you plug 0 into the tangent of 5x, what do you get up? Then you get 0. How about sine of 0? Yeah, so I'm just going to put underneath this, that, or on the side, that this is a 0 over 0. Usually, you say you use this rule of putting an h over your equal sign. I'm not going to make you do that, but I'm going to do it. The h saying L'Hopital, like the h in his name. Okay? And you have to leave your limit signs there because you haven't taken a limit yet. And then you limit and you do the ratio of the derivatives. So what's the derivative of tangent of 5x?
5 secant squared of 5x.
5 secant squared of 5x. What's the derivative of sine of 3x?
3 cosine of 3x.
3 cosine 3x. Look, you can't forget the chain rule. Okay. And now can you plug in 0? What's secant of 0? So secant 0 is 1 over cosine 0, which is 1. So the numerator here is going to be 5. And the denominator is going to be 3. Does that make sense? So that limit is 5/3. And that's because secant of 0 is 1, and cosine of 0 is 1. So when you plug 0 into this part and this part, you get 1 for both of them. Okay? We had no other way to do that limit, did we? No. Okay. All right, how about this one? Can you plug in 0? What do you get when you plug in 0? Do you get 0 over 0? What do you get?
It's
1 over
1 over e to the 0. Yep.
and that's 1 over 1.
Uh-huh. 1 over e to the 0, which is 1. It will be wrong if you use L'Hopital's rule. So, like, for example, you would have gotten 0 if you did it with L'Hopital's rule. Yes? Yep. Okay. So the first thing you should always check is, when I plug in the number, do I get 0 over 0? If so, proceed. If not, you can maybe say the limit is right away. Okay? Okay. So this one, what happens as x goes to infinity to ln of x and x cubed? Where do they both go? They both go to infinity. They go there really slowly, but they do actually go to infinity. So this is an infinity over infinity limit. And this rule also works for these functions. All right, what's the derivative of ln of x? And what's the derivative of x to the 1/3? Yep. 1/3 x to the negative 2/3. Okay. And before you go crazy, and apply the rule again, because you technically could, now it's a 0 over 0 thing, simplify this. Okay, so before you go nuts and apply the rule again, simplify it. But what I mean by that is take this expression, write it as 1 over x over 1 over 3x to the 2/3. That's the same thing, right? You've got a fraction over a fraction, how you deal with fractions over fractions. Multiply by the of the denominator, yes. So this is the same thing. Oh, and I'm sorry, I put an h there when there should not have been an h there. That should have just been an equal sign. Limit x goes to infinity 1 over x times 3x to the 2/3 over 1. And then does that simplify anymore? Yeah, the exponents can subtract, right? So what's 2/3 minus 1? Negative, so that goes in the bottom then, right? So that becomes the limit as x goes to infinity, 3 over x to the 1/3.
So if an exponent is negative, it just swings up or it swings down.
Yes, it just moves it. And I think this is going to be 0 now. Because as x gets large, x to the 1/3 also gets large, right? 3 divided by a large number gets close to 0. Does that make sense? Okay. So watch out for little bits of algebra that could occur, okay? Also notice that what we're doing here is we're finding horizontal asymptotes, aren't we? Like if I were to say look at the graph of the function y equals ln x over x cubed, it has a horizontal asymptote of 0, right? Let's just find asymptotes of things that are weird. Okay. All right, now sometimes you can have to apply the rule more than once to figure out what's going on. So at this point in time, what kind of limit is this one? It's infinity over infinity. So limit x goes to infinity. You differentiate the top, which is derivative, it would be 2e to the
2x.
Over
2x.
And those 2's could cancel, doesn't really matter, but they could. Limit x goes to infinity, e to the 2x over x.
I've noticed a problem.
Yeah, and the problem is it's still infinity over infinity. Do you see, does that make sense? So what do you think you do? Do it again. Limit x goes to infinity, 2e to the 2x over 1. And now what can you say is happening? It goes to infinity. Nope, you can just take the derivative. You don't have to label them. You can just say that, like, okay, if you use the little h thing, tells me that you've done that. Does that make sense? It says you've done this rule where you take the ratio of the derivatives. It's kind of a cool rule, isn't it? Does anybody do computer science in here? Have you heard about big O, like order of operations and how long operations take? Yeah, so that you know, e's, exponentials have a lot more, right? They're a lot larger than squareds.
So as long as the limit maintains its infinity over infinity or 0 over 0, you can do this rule again?
Yeah, as long, and you could be more than 2 times. Yeah, so as long as it maintains, but the only caveat I would say is make sure that you've simplified the expression before you do that. Like on the previous one, where we had the cube root and the ln, if you didn't simplify and tried it again, which you could do, it's just going to get really ugly. Does that make sense?
Yeah.
Okay. But yes, it can be applied repeatedly. Like I think this one's going to need to be applied repeatedly, and I suspect 3 times. Okay, so first of all, is it 0 over 0 to start, or infinity over infinity? I think it's 0 over 0, because tangent of 0 is 0, right? So this is limit x goes to 0, secant squared x minus, what's x's derivative? 1, great. All over 3x squared. Yeah, is it? I'm not sure. Tangent squared x plus 1 equals secant squared x. Sure, the top is tangent squared. You don't have to do that, though. What do you want to do? Do you want to make the top into tangent squared? It doesn't matter. But you could. That would be correct, okay? So is it still 0 over 0? It is, because when you plug 0 into secant, what do you get? 1, and 1 minus 1 makes 0, right? So apply the rule again. Now, the tricky thing is taking the derivative of secant squared, not so easy, right? Bottom is 6x. So if you differentiate secant squared, that's 2 secant x times
Secant x tangent x?
times secant x tan x. And I swear it's just one more time, okay? So first, can we at least cancel some numbers? The 2, okay. Can I write that as secant x squared times tan x? Was that okay with everybody? Okay.
What you were saying before is it's easier to simplify before you do it again.
Yeah, but this one, even that really isn't going to do all that much. This one's pretty gross, because the repeated derivatives just get tricky. Okay. This will be the last time we have to do it, because once you can see when you do it one more time, the denominator is going to become 3, which means it's not going to be 0 anymore. So what rules do you have to use to take the derivative of the numerator? Product and chain. So the derivative of secant squared will be 2 secant x times secant x tan x times the tan x plus secant squared x times secant squared x. Ask yourself if you believe that, but well, notice how this matched that, right? So derivative of secant squared, we just did it again, right? Okay, now you can plug in 0. And look at that first term. Without even simplifying, when you plug in 0, the secants will be 1, but the tangent's going to be 0, so that first term goes away. The second term is going to be 1, and then over 3. So this limit is 1/3. So moral of the story is repeated derivatives could just get kind of gross. You got to remember your derivative rules. Yeah.
So can you just look at the first one, the limit, know how many times you're going to have to do it by seeing?
Often, but not
Whether or
often, but not always. So yeah, if that minus x hadn't been there, you would have only done the iteration once before you would have run up against the wall, but unable to do it again because the limit wouldn't have been 0 over 0 anymore. So it depends. It is often the case that the number of iterations you need matches the denominator's degree, but not always. It's kind of like the worst case scenario.
That it doesn't, you mean?
It's the worst case scenario that it does. Like you do it 3 times when this was an x to the third in the bottom. Okay. So is this currently a 0 over 0 limit? Or infinity over infinity? I think it's 0 over 0, because you've got 0 times e to the 0, right? That's 0. And then 2 to the 0 is 1, right? And 1 minus 1 makes 0. So this is a 0 over 0 guy. What rule do you have to use to differentiate the numerator? Product, yep. So tell me what its derivative will be.
E to the x plus x e to the x over natural log of 2 times 2 to the x.
Do you guys agree with e to the x plus x e to the x? Over ln 2 times 2 to the x, you okay with that? One's derivative is 0. Okay. Now can you plug in 0?
Okay, 1.
I think you get e to the 0 plus 0 e to the 0 ln 2 2 to the 0. Is that okay? That's all right. I think you get 1 over, oh, that's ln 2 times 2 to the 0. So you get 1 over ln 2. Oh man, this rule's kind of fun, isn't it? I like this rule. This rule's good. Okay. Mostly I'm just making you review derivative rules and help you fix your tests. Okay. What's arctangent of 0? Oh, wait.
Or 1 plus.
I think I made a boo-boo to them. No, did I make, yeah, I think, no. ln of 0 is not 0.
Skip this one.
Isn't it undefined?
Yeah, this one is going to be, yeah, this one, I don't know how to deal with this one right this
0
instant.
over 2.
Yeah, it shouldn't have been pi over, yeah, and it goes to infinity either, because then it's pi over 2 over infinity. So this one we're just going to skip because I made a boo-boo. I wanted to review derivatives of arctan of 2x, but, you know, that was my goal. But, yeah, let's not do this one. Okay, this one isn't obviously a ratio. So, remember how limits can move inside of continuous functions? Like if you had like sine of some stuff, your limit can go inside of the sine function. You can limit the stuff and then do the sine. The same idea is true here. I've got the limit as x goes to 1 from the right, and this is natural log of the ratio x to the 4th minus 1 over x to the 9th minus 1. So that's using log rules, right? If I have 2 logs subtracted, it's 1 log. It's a log of the ratios, or log of the ratio. Now you're going to use that rule that that limit thing can go inside of the natural log function. Oops. Okay. And yes,
Does stating whether you're approaching the limit from the left to the right change what you get?
not the process. But you do have to do that in this case because from the other side, the ln function isn't defined. But it doesn't change the process as to how it works or anything. Okay, so is this limit currently a 0 over 0 or infinity over infinity limit? 0 over 0. So you apply L'Hopital's rule. Don't forget about the ln. And you get 4x cubed over 9x to the 8th, right? And at this stage, can you plug in 1? Yeah, what do you get? Yep, and the ln is still there, right? So I have natural log of 4 over 9. Okay. So the 2 indeterminate forms we talked about so far are the ones that are 0 over 0 or infinity over infinity. There are other forms that are not determinate. They are things like 0 times infinity. Much like you can't divide infinities, multiplying infinities by zeros, not always the same thing. So how you deal with this, you take your 0 times infinity. To use L'Hopital's rule, we have to make this into a ratio somehow. And you write this as one of 2 things, either infinity over 1 over 0 or 0 over 1 over infinity. And do you at least buy that that's kind of the same, those are equivalent things? So think about, I don't know, 2 times 6. That's the same thing as 6 over a half. Is that true? Yes. And 2 times 6 is the same thing as 2 over 1/6, right? That's kind of the pattern I've used here. Sorry. And the reason, thank you, the reason that that is helpful is if you rewrite it this way, 1 over 0 produces some kind of infinity, doesn't it? Positive or negative depends on the kind of 0, but it produces an infinity. What does 1 over infinity produce? Some kind of 0, and you've made the limit into something that you can use L'Hopital's rule with.
So you can't do it with zeros and infinity.
Nope, you can't. It can't be. This rule only applies to ratios, so that to use the rule, you've got to make it a ratio. And the other thing to remember is you're send the simplest thing to your denominator. It's going to make your life easier. There's going to be always more than one option, and both ways will work. It's just that one way might not work as nicely. And hopefully that will make sense when we do the next couple examples. Okay, we have 2 examples of this. And they all work more or less the same way. Okay, so here's the first one. This is the classic example. So this goes to 0 times, remember that natural log of x's picture looks like this, right? So as x goes to 0 from the right, where does natural log x go? Negative infinity. So how you change this into an infinity over infinity limit is this. You rewrite it as the limit as x goes to 0 plus of natural log of x over 1 over x. So the first thing you have to accept is that that is actually equal to the thing you had in the beginning. You're going to have to know to use this trick on your own because I now showed it to you. Does that make sense? Okay. And you think about 1 over x's picture. 1 over x's picture looks something like that, right? And now you have negative infinity over positive infinity. And now you can use L'Hopital's rule on this thing. But before that, you couldn't. Okay, so what's the derivative of ln of x? 1 over x, yep. And what's the derivative of 1 over x, or x to the negative 1? So negative 1 over x squared. Okay. And then simplify before you go crazy and do the rule again. Oops, and I keep putting h's over steps and I don't mean to. I'm so sorry. Equals limit x goes to 0, 1 over x times x squared over negative 1. So I think that's just negative x. Do you guys agree? So where does this limit go? 0 in this case. But the kicker is to use this rule, you had to make it a ratio. Does that make sense? That was the kicker. Mm-hmm.
So you can have negative and positive?
Yes, and that's okay. It matters that they're large. That's the real important part. It doesn't matter if they're the same sign of infinity. Nope, don't be the same sign. And by the part that I said in the last slide, I'm putting the simplest part in the denominator, you could have also done the limit as x goes to 0 plus x over 1 over ln of x. Like that would have also been okay. And that would have now been a 0 over 0 limit. But taking the derivative of 1 over ln x is harder than taking the derivative of 1 over x. So you see what I mean by put the simplest thing in the denominator? Okay, let's try one like that. So how would you rewrite this to start? First of all, is it an infinity times 0 is just going to go to infinity? So obviously this x is going to infinity, right? This sign of stuff, pi over x goes to 0, yes? So this goes to sine of 0, which is 0, right? So that's going to be a 0 times infinity thing. Which one do you want to put in the denominator? The x, yeah. So when you rewrite this, it's going to be sine of pi over x over 1 over x. And no, those over x's do not cancel the ones stuck inside the sign. So, shoot. And at this stage, what kind of limit do you have? Where's the numerator going? 0. Where's the denominator going? The numerator goes to 0 because pi over x goes to 0. Right? Pi divided by a big number makes 0. So sine of 0 is 0. Okay. Let's take the derivative now.
Would there be a situation where you still have to do the many times to get it to the?
Probably, but probably not going to make them that tricky. Okay, what's the derivative of sine of pi over x?
Cosine, or pi cosine? No.
Okay, so cosine pi over x, that part for sure, right? Pi over x is the same thing as pi x to the negative 1, right? So what's the derivative of pi over x?
Negative pi over x squared.
Do you guys agree? And then what's the derivative of 1 over x? Negative 1 over x squared again. Oh, and look, you should be really happy because what happens to the x squareds? They go bye-bye, and the negatives go bye-bye too. So this is the limit as x goes to infinity of pi times cosine of pi over x, right? And as x goes to infinity, where does pi over x go? 0. So this becomes pi times cosine of 0. Does that make sense? Which is going to be pi. Okay. So they shouldn't get much more tricky than that on your homework or your quiz, but just to know that I don't want to make them harder than that. That's hard enough. Okay. So how do you, so do you think infinity minus infinity is going to always be 0? No. We actually saw stuff like this. We did stuff like the limit as x went to infinity of things like root 9x squared plus 1 minus 3x. That technically is an infinity minus infinity limit, and we did that using a conjugate, right? Okay, so the two ways to deal with this might be to use a conjugate in examples like this, because that's kind of the only way I know how to use this, how to find that limit. I don't know any other way. Or get a common denominator, if that's something that's a possibility, like you have two expressions that are added or subtracted. And maybe the result of getting a common denominator might make it so that you can use this rule, okay? But there might be some homework problems where you have to use the techniques from a previous section. So for that one, you would have to use the conjugate. There's no other way that I know of. And you might be able to, after you do the conjugate, then you could use L'Hopital's rule on what you get, or you could just do it using the stuff we did before. But here's a couple that are not like what we did before. So this one is some kind of infinity minus infinity, because 1 over 0 plus makes infinity, and this one also ends up being 1 over 0 plus. So the first thing that I would say is you might as well get a common denominator, because what else are you going to do, right? So that's the limit as x goes to 0 plus sine inverse x minus x over x times sine inverse x, right? God, I hope this isn't awful. It might be. Okay. Limit x goes to 0 plus. All right, what's the derivative of sine? Can I use L'Hopital's rule on this thing now? Is it a 0 over 0? I think it is, isn't it? Okay. So So what's the derivative of sine inverse x? And then minus 1 over 1 sine inverse x plus x over the root 1 minus x squared, right? Do you guys buy that? It's x times 1 over the root 1 minus x squared, which puts the x in the numerator. Holy moly. So, oh man, can you plug 0 in? Will it work? When you plug 0 in, what is your numerator equal to? What's your denominator equal to? Unfortunately, your denominator is also 0 because sine inverse of 0 is 0. Right? Okay, do it again. Evil problem. Before we do it again, let's do this. Let's rewrite this as 1 minus x squared to the negative 1/2 minus 1. I'm pretty sure only one more iteration is going to be needed. Not that that makes you feel a whole lot better. And I would simplify this if I thought simplifying would help, but I don't think it's going to be super helpful. Well, maybe. Whatever. Do you see what I did there, though? Just wrote them as, okay. So use L'Hopital's rule again. What is the limit of the, what is the derivative of the thing in the numerator? 3/2. And then times what from the chain rule? Negative 2x. All over 1 over the root 1 minus x squared. And the next part needs the product rule, right? I promise you'll need this just once. This is the last iteration. 1 times 1 minus x squared to the negative 1/2
So we're,
plus x negative 1/2.
are you still going to 0 from the positive side?
Yes. 1 minus x squared negative 3/2 times negative 2x. Let's just simplify that a little bit. Like in the numerator, the negatives cancel, right? So do the 2's, yes? So you get x over 1 minus x squared to the 3/2. The denominator is, if I say 2 over root 1 minus x squared, does that make sense? Because I have this first thing that's 1 over the root of 1 minus x squared. This second thing right here is really 1 over the root of 1 minus x squared, right?
Yeah.
It's like x plus x is 2x, thing plus thing is 2 thing. And then plus x over 1 minus x squared to the 3/2. And I swear at this stage, you can just plug 0 in. Like, it's okay now. When you plug 0 in the numerator, what do you get?
1 over,
You get 0 over 1, which is 0. It scares you a little bit. You're like, oh crap, one of them's 0. What about the other one? But when you plug 0 in the denominator into that first expression, what do you get?
2 over 1, 2.
So 2. And then plus another 0. So what is 0 over 2 an okay thing to do?
Yeah.
Yeah, that equals 0. I had a student once who had a hard time remembering where the 0 could go because, like, dyslexia rules, and this was their helpful thing. Like the O is like the 0.
That's cute.
Isn't that cute? Yeah. They had to remember that OK was equal to 0, but yeah, it was a pretty cute trick. Yeah, it's okay versus no. I like that one. Okay, so I'm so sorry for this problem. This one hopefully is not as bad. This one isn't obviously a fraction, is it? But whenever I see cotangents and cosecants, I'm like, ugh, gross. Let them be sines and cosines, right? So limit x goes to 0. So cotangent is what over what? Great, cosine over sine. And cosecant is 1 over sine. And look, they already have a common denominator. Yay! This one will not be as ugly, I promise. That's cosine x minus 1 over sine. Is that okay? All right. Now, when you plug in 0, do you get a 0 over 0 thing going on? You do, because cosine of 0 is 1, and 1 minus 1 makes 0, right? So this is 0 over 0, and apply your L'Hopital rule. Numerator's derivative is negative sine, right? Denominator's derivative is cosine. And is it okay or is it no right now? It's okay. It's a minus 0 over 1, right? Which is going to be 0. Okay. Now the final indeterminate form is the trickiest. I'll make you do one on your quiz. Promise, promise, promise. Okay. This has to do with indeterminate powers. So if you raise 0 to the 0, 1 to the infinite power, or infinity to the 0 power, those are not always the same thing either. Basically, doing stuff with zeros and infinities, all bets are off. And so how you deal with these is you use logs, specifically probably ln. Specifically use ln. And it's a little bit convoluted and tricky as to how it works, but I think I can help you make sense of it. Okay. So here's an example. So this thing, first of all, it's 0 to the power of infinity. Does that make sense as to why that's true? This x is obviously going to 0, right? 2 divided by a little positive number makes a big infinity, right? That's a 0 to the infinity form. Okay, so how you deal with this is you start by, I'm going to always let y equal x to the 2 over x. Like this is the thing that I have. I'm just going to give it a different name. And then I'm going to natural log this. And what that might do that's helpful, it's going to take this exponent and make it into a product. Does that make sense? This becomes ln of y is 2 over x times ln of x. And that's now 2 ln x over x. Now, can you find the limit of that thing? So here's what I'm going to say. The limit as x goes to 0 plus of natural log y is equal to the limit as x goes to 0 plus of 2 ln x over x. Yes? Does that part make sense? Can you use L'Hopital's rule to find the limit of the, shoot. I feel as if I must have made a typo in this problem. It seems, because right now there's an issue, which you could fix probably. I don't want to try though. Let's make it easier by making this 0 plus into an infinity, okay? Because I didn't want to make this problem this tricky, so just make those infinities. And instead of being 0 to the infinity, now it's infinity to the 0. Okay. I wanted it to be an easy application of L'Hopital's rule, not a hard one. The next one's a bit harder. So can you use L'Hopital's rule now? So what's this limit going to equal?
Over X.
Uh-huh, over, uh-huh. And that's going to be 2 over infinity, which is going to be, as x goes to infinity, this is going to 0. 2 divided by a big number makes 0, right? You know that. Okay, so thus the limit as x goes to infinity of natural log y is equal to 0. What you want is the limit as x goes to infinity of y, without the ln there. So the technical thing that you have to do is this limit can move inside the ln. And how do you undo that ln? You e it. So the limit as x goes to infinity of y is going to be e to the 0, or 1. So in that case, infinity to the 0 power was 1. But because you've ln'd your expression, you're going to always have to e your answer to get what the limit's equal to. You have to undo that ln'ing. The ln'ing lets you find the limit, and then you undo the ln'ing by e-ing. Yes.
The actual limit is 1.
The actual limit is 1. Yep. The limit that you got was 0 was the limit of the natural log of the expression. That's what this is saying, limit of natural log of expression, right? So to find the limit of just the expression, you have to undo the natural logging process that you did to make the limit findable in the first place. That's the one tricky step. Does that make sense? Okay, let's try one more that hopefully isn't super disgusting. Oh man, okay. Let y, I'm scared. 1 plus sine of 2x to the tan x
But isn't this not 0, 0, or infinity over infinity?
not until you,
Because sine would be 0 and tan is 0.
so it's 1 to the,
0, which is 1.
yes. I goofed twice. I'm sort of disappointed in myself. Well, we can just be done then with that one.
Was it good?
Yeah.
I already started writing that one, though.
Yeah, well,
I didn't
you
even
could,
miss that.
yeah, we should not do Ellen if you don't have to. Because that would be, that's needless work. Yes, so it is 1 to the 0, which is definitely 1.
What if we did the whole Ellen thing?
I
Would
think
that come up
you
with 0?
probably would get the right answer, but I don't know. Yeah, I did it that way and it was painful. So don't do it that way. The end.